We're starting our unit on energy and thermodynamics. And we've talked a lot about energy through our units. We've talked about delta H, which is our enthalpy, and we've seen that on our potential energy diagram. So let's do some review. First of all, energy is the ability to do work, and that has to do with thermal energy, pressure, volume work. Enthalpy is actually internal energy and pressure, volume work. Internal energy is heat and pressure and volume. But we do this at constant pressure and volume, so really our heat energy is our enthalpy when we're talking about chemical reactions. Now, when we're talking about heat, we're talking about kinetic and potential energy. So our kinetic energy is that movement. So here I have drawn a steel bar and I put a candle under it, and what that does is it makes these molecules here that's right under the heat move faster. And this heat is transferred by collision. So as these particles move faster, they bump into these particles, which bump into these. And as my energy is transferred, things start moving faster and faster. And that's why that bar will heat up all the way through. That's why we don't use a metal spoon when we're cooking, but we have some plastic on the outside. And you can see it starts slowing down here. I have one woozy here. This means movement. I have three woozies here. That means they're moving faster. And so our energy is transferred from hot to cold, and this is our thermal or heat energy. I start by putting energy in on this side. It gets transferred all the way through that steel bar, through those collisions. And remember, kinetic energy is the energy of motion, and it's written KE or EK. I just wanted you to see both, and that's 1/2 mass times velocity squared. So if we're moving faster, we have more kinetic energy, or if we have more mass moving faster, we would have more energy. Potential energy are those the energy stored in those chemical bonds, and that has to do with the arrangement of those atoms, and we've seen the potential energy with the distance between bonds. Remember, there's a sweet spot, and then if they get too close, those electrons repel and we have a high potential energy. If they get too far apart, we have zero potential energy, and we had a graph that went like that. It was about distance. Actually, it went all the way up there. And so we can get some of that energy through those arrangements, and that's like when we burn gasoline, we are rearranging those molecules, and that arrangement gives us a certain amount of energy. So our units for heat energy is in joules. It used to be in calories. That was the old system, and it is how many calories does it take to raise 1 gram of water 1 degree, and 1 calorie is 4.184 joules, and the standard was water. It took 1 calorie to raise 1 gram of water 1 degree, so that's actually the heat capacity of water. A nutritional calorie is actually a kcal. It's 1,000 calories. So when we eat food, we get energy as well. Endothermic versus exothermic. We've done a lot of work on that. Exothermic is when energy is leaving or exiting the system. Endothermic is when energy is entering the system. And when we do a chemical reaction, it's happening in that beaker, and it's super easy. We can feel that beaker gets hot. It's giving off energy. It's exothermic. We can feel the beaker's getting cold. It's sucking the heat from our hand. It's taking heat from the surroundings, and that's endothermic. So we must define this system, and I'll show you why that's important in a second. But right now, our beaker is the system, that reaction vessel. And the surroundings is everything else. That includes the glass of the beaker, the outside air. And remember, conservation of energy, energy is not created nor destroyed. So when I'm heating up something, it will go into the surroundings or into our system. Okay, so now what gets harder to determine if it's exothermic or endothermic are phase changes. So when we melt something, okay, we take our water as a solid and we add heat to it, and that turns the water into liquid. And since we're adding heat to it, it's endothermic, okay? Condensation, we have H2O as gas. And then what happens is it forms liquid droplets, and that actually gives off some heat, and that's exothermic. So what I want to look at is why it becomes difficult and we must define our systems when we're talking about phase change. Let's take a cup of soda here. Here's my cup. Yes, I'm a wonderful artist, and here are my 2 cubes of ice, and they're in this liquid soda, okay? Now, if I feel this glass, it feels cold, so you just say it's cold, it's endothermic, but that's not true because we're not defining our system. We have 2 systems here. We have the soda, and my soda is getting colder, okay? And we have ice melting, and our ice melting is changing phases, and it has to melt by accepting heat into it, okay? So which way is this heat flowing? Well, the heat from the soda is going into the ice, and that's helping that phase change. So if our ice is our system, our heat's flowing into the ice, and that's endothermic. If our soda is the system, heat is leaving the soda, it's exiting, and that's an exothermic system. So you need to be careful to define your system to decide if it's going to be endothermic or exothermic. Okay? Our first law of thermodynamics is energy is conserved. It's neither created nor destroyed. So if I add heat to this beaker, the heat is, I should actually do this, it's going into the air, it's going into the beaker, okay, it's going into that glass, it's going into the water, and then the water is actually expelling some heat unless this was, unless we had some insulation around there to keep it all in, okay? So now we're going to talk about calculating that enthalpy or heat of reaction or heat of phase change. So here is our phase change diagram, and we'll make it water. So water freezes at 0 degrees and it boils at 100. And when we have a phase change, we don't have a temperature change. So if we're melting, that's delta H of fusion. Okay, and freezing has another thing that they really don't go into too much in AP. When we're vaporizing, that's delta H of vaporization, and when we're condensing, that's delta H of condensation. And so I can calculate how much heat energy I have to put in to melt a certain amount of ice. Okay, now our phase change, our delta H's are in kilojoules per mole. So if I ask you what is the heat energy needed to boil 2 moles of H2O, and I have the delta H of vaporization is 40.67 kilojoules per mole, I just take that many kilojoules per mole, but I want to boil 2 moles, so I multiply it by 2, and I get this much heat per mole needs to be, or actually that much heat needs to be added. Kind of did that wrong, just kilojoules because we have it for 2 moles. Okay, and now that just does this part of our phase change. That's just our phase change part. But then there's this part where we're not changing phase, but we are raising the temperature. So how much heat does it take to raise the temperature for this portion of the graph? And we use Q, which is heat, equals mc delta T, where M is the mass, C is the specific heat capacity, and delta T is the change of temperature. Okay, and our specific heat capacity is how many joules does it take to raise 1 gram 1 degree C. Now for water, we already learned it was 4.184 joules per gram degree C. That's how much heat it takes to raise 1 gram 1 degree Celsius. Okay, so we can calculate this portion of the graph. So your question would be, how much heat does it take to raise 2 moles of H2O, a liquid, which we're going to say is 36 grams. We're going to round that from 0 to 100. Okay, so we're figuring out this part of the graph. So we just plug it in, plug and chug. Q equals mc delta T. Our mass is 36 grams. Our specific heat capacity for water is 4.184 joules per gram degree C, and we're raising it. Our delta T is our change in temperature, so that 0, it's 100 minus 0 degrees. Okay, you could have a different range there. So our change is 100. Don't think that's because I gave you that 100 there. It is the change. Okay, so if I went from 50 to 100, my delta T would be 50. Okay, so make sure you have that clear. And what I get is about 9,600 joules is what it takes. So if I put both examples together, I can figure out, I changed my example there. So what we did was we figured out how much energy to boil the 2 moles to get it to completely change into gas. And if I put these two together, I can figure out how to bring 2 moles of liquid water at 0 degrees C from 0 degrees C all the way to the gas phase by adding those 2 numbers together. So in this phase, we have Q equals MC delta T, and for this phase, we use my delta H of vaporization. Okay, so when I put it all together, we're going from melting, we're going from raising temperature to gas. Okay, and we add those numbers together and we get roughly 9.7 kilojoules.